right? Actually, some problem you cannot solve in 3 dimensions. You are reducing to 2 dimensions. Or some problem you cannot solve in 2 dimensions. I'm not able to solve in 2 dimensions. So what I will do, I am projecting onto a line, a single dimension. So the single dimension, I can find the separation. In fact, this is called Fisher's equation, right? You have to find out the direction. Direction is nothing but the eigenvector, right? So you have to find the direction psi such a way that it is satisfying this Fisher's equation. This is an optimization problem. Maximizing J psi. Find out the largest eigenvalue corresponding eigenvectors. So we saw in the example itself, we saw what is SB, right? The between class scatter matrix. And also we have seen adding two S1 and S2. If it is multi-class, you have to add all the classes. You call it as a within class scatter matrix. Right? This is called the famous LDA algorithm or LDA approach. So now, right, what you are doing, you are determining LDA tree. You are not stopping the algorithm with LDA tree. Because any machine learning problem, you will not get 100% accuracy. Right? You might have seen in the literature 95%, 98%, 99%. Right? It is like I am not stopping my iteration with, let us say, single shot. That means only one iteration I am not stopping. I am continuing because I am not satisfied with, let us say, 95% accuracy. Suppose there are 4 classes, alpha, beta, gamma, delta. All right? So some of the delta points will occupy alpha. Alpha may be 95% correct. Right? So for this, what we do, let us assume that we are we are working on finding out the LDA tree. The same LDA algorithm, every node I am using LDA, right? So that I am making a tree. So that means I am doing more iteration. First iteration I may get, or in the case of a tree, we call it as a first level. First level I may get 95% accuracy. Then as the level goes, when I am reaching the leaf node, I may get 99.99% accuracy. So that is called the LDA tree-based algorithm. So coming back to the original problem, assume that I have 9 frames. And then you are finding out the corresponding skeleton. And then these are all the extracted features, right? The number of pixels I am calculating in each sector, right? I am placing like this. So this is a running sequence. My features are this. I am plotting it. Or I am calling it as a histogram, right? So now during classification algorithm, I have to match, right? Exactly how your mobile phone working in your binary class. You are putting your fingerprint, right? So you can see that it is scanning. That means it's training your fingerprint. So it is training your fingerprint and it knows that you are the owner, right? So now when you test it, right? Assume that you have given your fingerprint, it says 95%, 100% features I have taken. This is what you will get either in Android or in iPhone. So now you are testing. So when you are testing, again you are putting your fingerprint. So what will happen? If you are the owner, it will go inside. Otherwise, it will not. That means it is trying to match, right? It is trying to match the fingerprint. And then when you are the owner, yes, the binary class problem, yes, the fingerprints are matching. Otherwise, it is not matching. So here it is the running sequence. I am finding out the corresponding features. So these are all different classes, right? Running, walking, punching, right? These are all 20 different classes. And then, right, for example, here you have, let us say, different classes, right? Different actions you are seeing in the first row. And then the corresponding skeleton. And then third, you are finding out the features. Right? For example, if I use the traditional LDA algorithm, misclassification is more. Right? For example, sometimes you may feel, even after putting your fingerprint, you may not enter. Right? That is called the mismatch. Right? When I use the standard LDA, mismatch is more. Right? The second row, if you look, it goes even 5. Right? 0 is the best. And it goes 1, 2, 3, 4, 5 means misclassification is both. That means if I stop my LDA algorithm in a single shot, I may get a lot of misclassification. If you use a tree, the misclassification number is less. Right? So this is a visual human action SIL out data set. So from the data set, right, if I'm going back to the problem, this is the common parking lot area. And then experimentally, right, if you do, a person is walking, running, right, two arms are up, only one arm is up, sitting posture, right? So the second row is indicating the SIL out, that means the binary image. Third one is a skeleton. Fourth one is the pattern that I am getting, right? And then I will match, my LDA algorithm will match. For example, for a running sequence, machine knows only the histogram. And then the machine is matching where exactly I can match this histogram with the already trained data set, right? So then I am obtaining the classification algorithm. So for example, here we get 95.8% accuracy if you use standard LDA. If you're using a LDA tree, the accuracy is 98.5%. Right, so this is a standard machine learning algorithm. So now people are working on the deep learning algorithm. Right, it is also like, see, you might have heard, many are talking about AI, many are talking about ML. Right, so whatever I talk, the traditional machine learning algorithm 5 to 10 years back. So now the researchers have started working on the deep learning. The industrialists all are working on the deep learning algorithm. Right, so here you can find, right, I'll just complete my talk in another 5 to 10 minutes, right? So here, this is a video data set. So here you can find a person, right, is doing some action. So these are all different actions. So now I am planning to apply the deep learning algorithm, right? For example, a video is given, video is the input, right? And most of them are now wearing smartwatch. Smartwatch will also generate the data, right? So you may be knowing. Assume that we are generating a data from a smartwatch as well, wearable device. Video, wearable device, right? So from the video, what we will do, right? So we will find out an image. We call it as a stack dense flow difference image, SDFDI. Finding out the image. Train your neural network, right? We call it as a convolutional neural network. So you have a smartwatch, right? Assume that the data that you had seen, a person is wearing some wearable device, smartwatch. Apart from your video is one data, and wearable device is another data. So from the video, I am finding out the image, which is a 2D. So two-dimensional convolutional neural network, right? And we can find a skeleton, right? So three-dimensional convolution neural network. So apply 1D CNN, 2D CNN. CNN stands for convolutional neural network, right? Input layer, you are seeing 1D data, 2D image, and 3D skeleton, right? And then hidden layer, you are finding one-dimensional CNN, convolutional neural network, two-dimensional CNN, and three-dimensional CNN, right? That is called hidden layer. And then you have an output layer, right? So because three dimensions are there and we are fusing to common dimension, you get the output that is nothing but a class, right? This is how exactly the deep learning algorithm works, right? Any problem, right? So when you do this algorithm, we are getting 97.91% accuracy, right? Similarly, there are several interesting problems. Assume that a person cannot see the world, right? We fix a camera in the head mounted, right? We fix the camera here, and then the camera is connected to the mobile, right? This problem is called vision and language. In computer vision, this problem is called vision and language. So the vision will be from the camera. So what we are all lucky. We are getting from our eyes. So assume that a person cannot see the world, right? We fix a camera in the foremount. You might have seen Google Glass, or you might have Here Google Glass, right? So let us assume that a person is walking in the road where he or she cannot see, right? Assume that they are encountering these. So we call it as an ambulation, like a walking or using lift, or daily activities like drinking coffee or eating or doing office work or doing exercise, right? So here, right, we apply a deep learning algorithm, correct? I'm not going into the detail. So let us say input source is like a Google Glass, right? The glass is being wear, and then you have a wearable device. So it is connected to your mobile. So the mobile will, right, whatever scene has been captured by the camera, right, your mobile will talk, right? So you are near railway station. So you are inside the college. You are inside this room, correct? So this can be done based on the deep learning algorithm. For example, from the video, assume that we get approximate dynamic image, you call it as a ADI, and stack difference image, you call it as a SDI, right? So the architecture goes like this. So you have a video and you have a signal which is generated by the wearable device, train the neural network, right? The hidden layer, you are training the neural network, two-dimensional convolution neural network and one-dimensional convolution neural network, find out the classes, right? Walking, sitting, right? For example, if I'm going nearby a restaurant and I have some images, or I'm going near metro station, I have some images. So based on the image, assume that, right? You have to train the data, and then it will speak. The mobile will speak. Oh, you are nearby railway station, right? So this will assist the person who cannot see the world, right? So these are all the application, and here we are getting 86.5% accuracy when you use these kind of algorithms. And almost the last part of my talk, so I talked about these kind of video, right? So where it was taken with the infrared camera. So in the infrared camera, in fact, we are doing a project with the DRDO, right? So in fact, I am Uttarakhand is almost a border, right? So we have a DRDO lab there. So they fix a camera. So the camera will capture nearly 100 or 200 kilometers away images. Imagine, they have such powerful camera, right? So during night, so they have a camera during daytime, no problem. Okay, who are entering right into India or who are leaving or what is happening in the border, right? So imagine during night, it is slightly difficult. Or in the winter, the North Indian winters are very, right, it's very unbearable, right? So during that time, right, so during night, so for example, we have simulated this scenarios in our IIT Roorkee, right? Assume that a person is kicking, fighting, hugging, or carrying a gun, right? The simulated one, right? In this situation, assume that we fix the infrared camera, and then the signal will automatically goes. If any unwanted event happen, can the signal go automatically to the security office, right? This is what the target. So it will capture these kind of scenarios. So when you're looking here, right? When you are looking here, immediately you look for the persons only, right? The human vision looking for the persons only, what exactly they are doing. So immediately you will see. So the machine will do the same, right? Can the machine will do the same. So that means what we are doing, we call it as a saliency. When you are looking exactly the persons, right? In the previous image, you are exactly looking only the person. You are not worrying about the background. So that is called the saliency problem. So you determine stack dense flow difference image. Apart from that, you determine stack saliency difference image, right? Your video is the input. Infrared video is the input. The night vision video is the input. Train your neural network, right? That is what going on hidden layer. Divided into local and global. Stack dense flow difference image and stack saliency difference image, right? Fuse all the data together because you have a local and global difference image. So what you do, find out the in output layer will be the different classes, right? Input layer is the video, infrared video, and this is the training one. That means the hidden layer. And the output layer, you are getting the output, right? So this work appeared in infrared physics and technology, and in fact, the accuracy goes up to 75.17%. So these are all the practical problems, and in fact, I introduced the traditional machine learning algorithm where there are several mathematics. So I could focus because I have been given only 1 hour. So you look at my website and how I work both mathematics and computer science, right? So I thank, these are all some of the funding we are getting from DRDO, SERB, India, MATI, right? IITR sponsored some of the instruments, and we have done a work for Samsung as well, right? I thank all my lab students, right? We have a machine vision and machine intelligence lab, and thanks to Department of Computer Science and Engineering, right? I'm a faculty chair of IIM, Divya Sampak, and these are my lab website, and this is my email ID. The last one is my email ID. So thank you all for listening 1 hour without any disturbance. Thank you all. So if you have any questions, I am very happy to answer. Yeah, we have a open computer vision. We call it as open CV, and another one is Python. Yeah, when tie happens, you can have any one. Both are same. I think both will give you same eigenvector. So tie happens, you are going to choose one of them. Yeah, good question. Yeah, so to increase, right, you have to play with, right, more number of hidden layers. All right. For example, some authors may use only, let us say, 3 or 4 hidden layers. So try to improve, and then see, basically base and weight, you have to keep on changing in the hidden layer, B and W, right? So the whole neural network is based on that B and W. So you have to keep on changing the base and weight, right? Or you can increase the number of hidden layers. Or if you want to work on the traditional machine learning algorithm, you have to keep on switching your feature extraction algorithm and classification algorithm, right? For example, you may work with wavelet as a feature, and classification may be SVM. So now change to your geometrical feature extraction with, let us say, LDA, right? So one may give, let us say, 95% accuracy, you may increase to 98%. All right, so it's a machine learning problem is based on the trial and error. So you cannot say that this algorithm is the best. So you have to keep on changing, because in some applications, one feature extraction algorithm works perfectly, another may not work. Whereas the computer vision, the another one will work perfectly. The one it was working for the standard data may not work. So from student side, yeah, correct. Student side, any question? So you are all my juniors, you can ask. Yeah, please. The one I have given a linear separable. You can have a non-linear separable also. That's called nonlinear regression. In fact, you have a clustering problem also. It will be a mixture of classes. I have taken a simple example so that students may also understand, and I projected only the linear separable. Very easy problem. Yeah, you have a nonlinear regression and you have a clustering algorithm. All right. So most of this deep learning algorithm are nonlinear only, nonlinear in nature. It's not even need not be only linear separable. Square or rectangle, unnecessarily, we may have a lot of black pixels. That is advisable. If you fix a elliptic one, the number of black pixels now will be less. Otherwise, unnecessarily, you have to do the computation for, if you, let us assume that you're choosing a square or a rectangle. No, ellipse will give more accuracy. Problem will be simpler, right? Problem will be simpler. So ellipse will give more accuracy. No, any object is fine. Any object is, see, it is, that's what I mean. If you are okay, comfortable with the, let us say, square, or you can use all the geometrical entities, whichever is having, let us say, see, these problems are based on the experimentation only. Yeah, mathematical we have. So suppose, let us assume that you are fixing with a square, some objects, some other objects, what you are seeing a non-human objects. So suppose you are fixing with a square and the number of black pixels are less. Experimentally, 80% of your data, so the square is doing better, means you can switch over to square. Yeah, people have done with square. Many of the deep learning algorithm you can see in the video. So they try with the square or rectangle. Yeah, tree. So either you can converge. Let us say my target is 100%. So you get 99.99 or something. You can stop. Stopping criteria you're asking. You can go as many as, but yeah, the convergence criteria you put how I am reaching to 100%. Right. So for example, here in this case, 15 or 16 level, we used to get the convergence. Tree is a full binary tree. Full binary tree. It need not be binary if it's a binary class. So assume that it's a n-array tree, full n-array tree. So binary means you have only two classes, right? So in that case, it's called full binary tree. If it is a multi-class, it's called as a n-array tree, full n-array tree. Yeah, correct. Self-driving cars. Yeah. Similar algorithm. I mean, they are not using the same algorithm. Similar. See, there it's a 360 degree. If you look at the Google car, right? So they fix the camera and then 360 degree, right? It has the vision. So you have multiple images, right? In a second, imagine 360. You may get a huge number of images in a second, and then assume that it is going in the road. Every second, assume that it is having 80 is a small frame, 200 frames every second. So imagine I'm driving, I want to drive a 1 hour, right? 1 hour drive. So the huge video data you have, and then it will analyze. I mean, they have, right, all the algorithms, right? How the human is driving. So you have to see the signal, what are all the vehicle is approaching. So they have trained with a huge model. The system may work for a US kind of or abroad kind of environment, whereas in Indian roads, still we have to improve. Yeah, in India also we are trying. But yeah, in the agricultural point of view, you are right. The tractor and all, no? So in the agriculture, automatically that will do. So because the number of objects, everything is small compared to the huge data when you are driving in the road. Yeah, almost similar algorithms. They don't use the same algorithm, so it's a similar algorithm. Yeah, thank you so much. Yeah, yes, madam. 91 to 94, sir. 91 to 94, sir. So if Mahavir sir recommends, I may take one or two internship students. Okay. Yeah. To IIT Roorkee. Yeah. I'm giving full credit to Professor Mahavir. So you can do internship in IIT Roorkee. The first, first slide you have seen the picture of IIT Roorkee, right? So you can either travel or if you want to do online also fine, right? So professor has to recommend. Thank you all. Thank you so much. Yeah. Sorry. Yeah. Ah. Hmm. In the airport. Yeah, that is what you in the hidden layer. Either you have to increase the number of layers, or you have to keep on playing with this W and B, the weight and bias. All right. So that will do all the classification. See, for example, assume that it is a carrying a gun. That is a different class. So it will have the separate features. Right? You are seeing clearly. Correct. So each class, for example, dropping object. Right. That object, that image is completely different from the person who is clapping. Right. You can see that. So now, how we are determining, how the human is determining. For example, I am giving these two images. One is this, and second is this. Right? I am asking you to differentiate. Yes, in one case, the person is completely bent, and the second one is standing up and doing the clapping. Correct. So now, in the input data, you are giving like this. In the hidden layer, the features will be completely different. It is like a features will be completely different for apple, completely different for banana. Right? So this will be determined during the hidden layer, in the hidden layer. Right? So you have to keep on changing W and B. Yes, your question is right. So can we, yes, misclassification is possible. All machine learning algorithm don't give 100% accuracy. Right? So you have to end up with 99% also. But the challenge is from these two images, right? So in the hidden layer, with the help of this weight and bias, we have to try to find out. We have to try to converge. Yes, it is converging to drop object. It is converging to clamp. So hidden layer is very important in convolution neural network. Or if you are using a traditional machine learning algorithm, your feature extraction, right? The feature extraction part, we have to be very careful. And also during training, okay, we are keep on training. This is a dropping object. This is a dropping object. And clapping. This is clapping. So during training, the future, for both the cases, the future extraction is very important. So that future extraction will determine the classification. Explainability you can use in the emotion recognition kind of problem. Yes, we have done. If you please go through all my papers. So explainability algorithm also we have done for emotional recognition, which is a one-dimensional speech recognition problem kind of. For example, if I am talking, whether I am happy or sad, right? Or some students may be very sad in the class. How to determine this, right? So these are all explainability problems. Okay, thank you all. Thank you very much.